Hello, everyone. My name is Brodie Kurczynski. I am a software engineer at Las Cumbres Observatory. We're down in Santa Barbara, and I'm going to talk to you about real-time observations on our global network of telescopes. So, things that I'm going to be talking about today are Las Cumbres Observatory itself, my employer, the purpose of a real-time interface, and astronomical observation methods, and the real-time interface itself, the design, the architecture, and finally, a demo. And this little guy here, his name is Cyril. He is going to help us do the demo. He is Las Cumbres Observatory's mascot. All right, so Las Cumbres Observatory is a nonprofit that promotes astronomy through science and education. We specialize in gravitational wave discovery and observation of supernova. We have 46 employees, 9 of which are developers. We don't have a QA team or a DevOps team. All of those developers manage those different hats by themselves. So if you're a software developer, you test the code, you deploy the code, you run the code, so on and so forth. We perform time domain astronomy, and the way that we do this that makes us unique is we have a global network of telescopes. And that allows us to be the only observatory in the world to be able to make observations 24 hours a day. And I'll explain in more detail about some of the challenges we face with time domain astronomy, but it's basically the study of how astronomical objects change over time, especially those beyond the solar system. So here's a little map of all of our telescopes around the world. The legend down here shows that we have 2 meters, 1 meters, and 0.4 meter telescopes. So we have those at sites in Texas, Hawaii, Chile, South Africa, Tenerife in the Canary Islands, Israel, and Australia. We currently have 25 telescopes around the world, with 21, with 5 more being added at existing locations over the next couple years. And then over here in Tibet, we have 2 more telescopes that will be added as funding allows, hopefully, over the next couple years. Okay, so why do we want to build a real-time interface at all? So we're contractually bound to, actually. Las Cumbres Observatory acquired telescopes from the Fox Telescope project in the United Kingdom, right here. And on top of that, we want to promote interest in astronomy through education. So the observatories that we acquired, or the telescopes rather, are here in Hawaii and Australia. So it helps to be able to promote astronomy through education in these locations because, as you can see on the map, here in the UK, it's the afternoon. So right now at this time, you can't make observations in the daylight, but it is nighttime in Hawaii and Australia. So it's kind of cool to be able to make these observations during school hours for children to be able to learn. And the reason we need to create this alternate interface is because our interface for professionals are too slow and complex for general education. You can't go and explain to a school child all of the different location requirements, all of the different metrics that are needed in order to make professional grade observations. So, challenges in time domain astronomy, much like the screaming angry sun in Rick and Morty, the sun is the enemy. It's very difficult to study astronomical objects if they can only be observed in 24-hour periods. It's very difficult to go about and have your observation times broken up because of the sun. So the way that that can be alleviated and we can achieve 24-hour observing, it requires a global network of telescopes. Thankfully, we have that. And again, so the time right now, roughly now, here at this location is 1:15-ish. And so nowhere in the Americas right now can we make observations because it's daylight. But anywhere in parts of Africa and South Asia, we can because it's dark. Fortunately, we have telescopes there. So I'm going to cover over on the different methods of observing that are used in astronomy. The first one is classical observing. And so that's basically just what a lot of people think of when they see an observatory or hear about an observatory. It's when a person or group of people, of astronomers, go to an observatory site and they manage a telescope. They look at a telescope, make observations, and look at what they're trying to research. This is still used by many observatories around the world today. And the problem with it for any kind of astronomy is that it's expensive and time-consuming. And the reason for that is you need your group of astronomers to physically go to an observation site and make those observations. And that's very prone to faults, such as weather. You can predict the weather as much as you want, but when it comes down to it, oftentimes when groups will go out to make observations, they are hit with either skies that aren't clear, clouds, rain, so on and so forth. And additionally, classical observing is inefficient. And that's because astronomers have to go and generate these target lists of observations that they want to make in the sky by hand, and then manually go through there and make observations and make changes depending on things that are going to occur, such as weather or location of the observing targets. The next method of observing is what's called cued observing. And this is the primary method of observing used at LCO. And that's because it can be implemented efficiently. So unlike classical observing, there's no need for astronomers to go to a site. They can have staff at a site that astronomers interact with to actually make the observations. So it's still not prone to weather conditions, but it makes them a lot less costly than flying everyone out there. And you have the ability to automate tasks easier with this because there is less human intervention that needs to be made. When using cued observing, observations must be scheduled in advance. And so that can mean minutes in advance, months in advance, as long as you're able to predict where the object will be in the sky and to make an observation on it. And at LCO, we use software to automate this task, which is actually a lot more difficult than it sounds, because it's basically like a huge constraint satisfaction problem with a huge problem set. So you have numerous telescopes around the world, you have locations of the observations, weather, and then importance of these observations. So it's actually kind of a difficult problem to solve. And we actually, some years ago, we hired a person specifically to work on their doctoral project. Dissertation, yes, thank you, on their dissertation to solve this problem, and they did. So that's what we use. Most other observatories use manual processes for this, and that's because the astronomy community as a whole is very suspicious of software's ability to automate their tasks. They think that they can do it better, and they think that they don't trust it. A lot of the astronomy code bases that exist today are in Fortran, IDL. If there's not a huge reason to move forward, they just stay behind. If it works, just keep doing it. And so cued observing is the best method for professional observing because of the generally low overheads and the ability to automate. The last type of observations that can be made is what's called real-time observing. And real-time observing is basically like an astronomical point-and-shoot camera. There is no expertise required. So just like those little point-and-shoot cameras that you can have, pull it out of your pocket, shoot, done with it. You don't need to know about any exposures. You don't need to know about anything fancy to make the camera work, make the telescope work in this case. And this is cool because you have nearly instant results. Making a single observation as fast as possible, as opposed to making it as detailed as possible and used for research purposes. And so real-time observing is excellent for education purposes, but unfortunately it doesn't have the configuration, or it's very difficult to enable the configuration for professional grade astronomy. So Comparing the two different observation methods, we have queued observing and then we have real-time observing. So as I said, the queued observing is great for professional grade astronomy and the real-time is great for educational purposes. And that's because the workflow of a queued observation goes that an astronomer will submit a request for an observation. That observation will be scheduled, or that request will be scheduled, and then the observation at some point will finally be taken. The image from the telescope will then be processed and then sent back to the astronomer for research purposes. So this whole system, depending on the location of the telescope, the location of the object in the sky, and the processing time of the image, or excuse me, the exposure time of the image, takes about 15 minutes, which is great if you have this running readily, if you're able to fire and forget from an astronomer's point of view, but you can't have school children wait 15 minutes or like a few minutes for that matter for this process to work. Very antsy and won't follow along. So we went to solve this problem with our real-time interface. That workflow looks more like a teacher will request an observation, and then the observation will be taken. And so images from this workflow are sent back in as little as 10 seconds. And again, there are varying factors that can happen based on location of the target, slew times of the telescope, the time it takes for the telescope to move to a target's position. But it can be anywhere. It's on the order of sub-minutes or minute. And then while that's happening, and there's something that is able to be seen there of an observation that's been taken, the image is processed, just like in the queued observing, and that whole process of a finalized process image takes roughly 2 minutes. All right, so in designing this real-time interface, we had a few design objectives that made it unique for us. One was it had to be a lightweight implementation. We didn't want it getting tangled into our existing infrastructure. The second is it has to be a simple interface. It has to be easily understandable for school children to be able to be interested in, and for general teaching to be able to understand and use it. The next one, it has to be a drop-in to our current infrastructure, and it has to be able to access part of LCO's private network via the internet. So it has to be accessible from over in the UK at the educational facility, but we still want them to have access to part of our network. And then one of the biggest things for us was stateless authentication. We don't want to create a new credential store for this use case. We already have the astronomy, the credential store for the astronomers, and we don't want to get this tangled in or have any special cases where we're resetting passwords for teachers or school kids or anyone using this. We want to be able to hand this off to an external admin and then have them deal with all of that trouble away from us. And the last part of our design objective is that we need to enforce observing session times. So these sessions must be scheduled in advance. Since we do have a global network of telescopes, they're being used for science purposes almost all the time. And so for these educational sessions, we don't want them to be able to step on the toes, so to speak, of those observations. So we have to make sure ahead of time to agree upon a point at when these education sessions will happen. So the first design objective, lightweight implementation. We went through this by creating a web portal that is responsible for handling authentication input and output from the internet. It is also responsible for observation input. So what targets are you going to look at? What kind of exposures do you want it to take in a very simplified fashion? And then you also want to display the telescope status. So basically what's going on when you make these observations, kind of keep kids interested in what's going on there. And for this, we chose Bootstrap and Vue to develop this. And we chose Bootstrap because it's CSS that allows us mortals to be able to use CSS. And Vue because it's very small and intuitive, especially coming from an object-oriented background. The next piece is the bridge of the real-time interface. And this is the thing that, or this is the piece of software that bridges the internal LCO network to the internet and helps us securely interface between it. And it does that by generating authentication tokens from the external admin of LCO and authenticate those sessions that they create. And for that, we chose to use Python because it's easy to use for web frameworks, and we chose Flask over Django because what it's performing is very simple for what we need. We don't need the complexities of Django for this. And the last thing in our implementation that we needed was a queue. And this is to communicate from the bridge to the telescope at an observation site. So the telescope commands would go from they do go from the bridge to the telescope. And then when they wait on the queue, telescope commands are executed, and then the telescope sends back the status of those commands back to the bridge and then over through to the portal. And we chose RabbitMQ to implement that simply because it's fast and easy. It's exactly what we need. Okay, so the next design objective is to have a simple interface. So on the left-hand side here, this is what the astronomer portal looks like for observations made at LCO. And there are a huge number of configurations. There's about 25 configurations on this. Anything from general configuration to target configuration. There's numerous configurations available, which is great if you want to do professional grade astronomy, but it's too complex for the general public to use. So on the right-hand side is what we developed for what we thought was a simple interface. So this is the real-time interface portal. It has the basic status of the telescopes here, and then a target selection here, and that's it. So the only thing a person needs to know is what target they want to look at, which they can come through from a drop-down, and then be able to read the status in very simplified terms of how the telescope's working. And then there's some other stuff like what it looks like inside the observatory and what it looks like right outside of the observatory in what's called an all-sky camera view. Okay. Another objective, or excuse me, another design objective that we had was that being of a drop-in architecture. So the workflow of our existing architecture is an astronomer goes and makes an observation. It goes through the observing portal, in through the scheduler. The schedule is stored into a database and then sent out to different locations to the telescope to actually make these observations. Again, this is very complex to go through this for an average person, and it takes a bit of time. The other method that we have of being able to make observations is what is using what's called an engineering interface. And that's what the developers and engineers use to interact with the telescope. This is even more highly complex, and it's actually kind of difficult to use. The only reason it exists is so that the telescopes can be debugged and tested. The final workflow is for the real-time interface for a teaching person to be able to use. And so this goes and sidesteps all of the existing architecture because we don't want any of the complexities and we don't want any of the difficulties to go through there. So as I showed in the last slide, there is the web portal, the bridge, and the queue that talk to the telescope to make observations. Next design objective, stateless authentication. We don't want to handle user accounts, so what we chose to be able to securely distribute these observing sessions are using JSON web tokens. And the JSON web tokens allow us to have no need for user accounts. We're able to have observing session information securely stored inside of these tokens. So we don't have to worry about comparing them or validating them against different credential stores. This is also helpful for us because it requires a password to generate tokens for the observing sessions. So we're able to give that to an external admin to handle by themselves. So this password is distributed from LCO to that person. And all of this is great because it's near zero LCO authentication management. The only thing that we have to worry about is distributing the password to the admin that's external, and then create the observing sessions that just match up with the education partner and us. That's it. No database management, no authentication management. Simple. And I believe this is the last design objective. We want to be able to enforce the observing session times. So how do you do that if you just have a single token? That's easy for access to, say, another database to have this information stored in it, but we don't want that. So the contents of a JSON web token look like this, as an example. So in it, it's just basic JSON, and the user ID is there. And this is used just for a display name to be shown on the control interface itself. And then there is information of the telescope, which is just, it's not unique. It's just like a display name of the telescope to kind of give the user a feel of what telescope they're using. And then there's the telescope address, which is an address space that we give each one of the telescopes. And this must be unique per telescope. It's kind of similar to how like URLs work. And then finally, second to finally, these are the observing sessions in here. So once a token is created, it is encrypted with the password distributed to admins external to LCO. And these active session start and active session end times cannot be changed because the token itself is encrypted. So it can be verified on the bridge end, but it can't be modified without the password. And then finally, this is the password that must be validated in order to ensure that they have rights to create the password, or excuse me, generate the token in the first place. And that's what one of these JSON web tokens looks like. So this is what the admin will distribute to anyone who's going to make an observing session for education. Okay, so bringing all of this together, we have two different use cases for the real-time interface itself. There's the admin that I spoke about, and then there is the teacher. We have the portal that we created, we have the bridge we created, and the queue. So this is our real-time interface. And then this interacts with the telescopes at the observation sites, which I talked about, which is a completely different beast and could talk about for hours. So if we just focus on what happens in these interactions for the real-time interface, we have an admin that submits the password all the way down to the bridge. The bridge validates that, and then sends the admin back a JSON web token, just like the one in the last slide, to be able to authenticate educational observing sessions. Then it's the admin's responsibility to pass that token over to the teacher, in which they can use this token for observing sessions. So that token is then used, validated with the bridge, and at which point the teacher can start sending commands all the way down to the telescope. So it goes through the web portal, the bridge passes it off to the queue, and the telescope itself picks up the command and then executes these requests of whatever was sent to it. Once that finishes happening, the telescope goes and sends back the status all the way through the real-time interface back to the teacher, and it pops up on the web portal and allows them to educate children. Okay, so now I'm going to try deeply to do an observation example. So right now, at all of our telescope sites, it is light, except for one in South Africa. So I've created a session that we will make an observation on. Okay, so this is the admin interface that the admin will go to. You have your user ID. Then we have a test telescope, because this is the only one that's dark right now for us. We put in the date that we want it to be valid, and these are in UTC. So we'll go and start it at 8. And we'll go on to 9. This is the password that's distributed for the admin. And then we generate the token. Send this off. And there we are. So we are connected to our observing site in South Africa right now. This is the all-sky camera. That's what the sky looks like right now, just out of a camera view, not an actual telescope view. And then, as you can see, right here, the session is in progress. We created a token for 1 hour that expires at 9 o'clock UTC, so we have 20 minutes remaining. And the observatory is available, and the telescope is still tracking, so it's locked onto a target, probably from a previous observation. And then the camera is idle, ready to make our observation, and our progress is ready because we're ready to make an observation. Now, this most recent image here is left over from a previous session because the way the telescope works at the sites, it has a queue of all of the images that have been taken. And it wasn't a requirement for us to make sure that these were strictly adhered to the real-time observing sessions. So we just left it at the previous image that was available. The internal website camera, webcam at the site is down because of maintenance. And so let's choose, I think, M66. Oh, M66 is not available. Okay, so let's look at M6. So we're going to choose a filter for this, and we're going to expose. So it goes, starts up, and there you go. So our telescope right now in South Africa is executing this request to make an observation on M6. So the telescope's moving to a target. The camera is getting ready. It's configuring. And let's see. Now it's tracking. So it's locked onto the target and it's tracking, and hopefully we'll start exposing soon. Yep, there we go. So it's a 20-second exposure. So it's tracked on to the target and is exposing for 10 more seconds. So these are the kind of things with like the flashes and how quickly it responds that kind of keep children's and even myself's attention span, or it keeps their interest with a very short attention span. And so now it's done. It's made the observation, and as you can see, it's reading out. So tracking idle, and there is the image that we just took, and now it's being sent back to our headquarters over in Santa Barbara, and it's going to be passed along right here and spat out as soon as it's finished processing, which should just be a few more seconds to see. Okay, so that'll show, oh, there we go. And there you go. We just made an observation in South Africa over our real-time interface and took this image with it. So yeah, that's how simple it can be for educational purposes and the general public. And that's my talk. So if anyone has any questions, be glad to answer them. Yes? What, sorry?
Development time frame?
The development time frame for this was maybe like 2 months or something. But that was with 2 developers, about the time of 2 developers. Yeah.
What happens to the previous job that was tracking when you sent in your instruction?
So that's a good question. That's a part of the time slots, the observation time slots that I was talking about. So normally the observations are scheduled, and we have to set time slots that things don't get scheduled. So like for right now, for this demo, I went and said, okay, between these times, don't schedule anything, and it allows us to use it freely. All right, if there's nothing else, then thank you very much, everyone.